Have you ever paused for a second and just wondered why the physical world around us works the exact way it does? I'm talking about those invisible, unspoken rules that govern literally every move we make. In today's Explainer, we're going to crack those everyday physics mysteries wide open. We're talking about the fundamental forces shaping our reality, plain and simple. Our goal here today is pretty straightforward. We're going to uncover the laws of nature by exploring 5 fundamental physics concepts, and we're going to do it using relatable, everyday examples. So no heavy academic jargon, no confusing textbook formulas, just pure, structured understanding of the world around us. If you're ready to see your daily routine through an entirely new lens, well, you are definitely in the right place. Okay, let's dive into this. Here is our roadmap for this explainer. First up, the secret of continuing motion. Second, why bus passengers lose balance. Third, friction as a double-edged force. Fourth, the truth about falling objects. And finally, exactly what happens during collisions. All right, let's kick things off with Section 1, the secret of continuing motion, or simply put, why things keep moving. Imagine you're pushing a really heavy crate across the floor. You push it, it slides, and then you just totally let go. The force is gone. But the crate, it keeps moving for just a bit before it finally stops. Why doesn't it freeze the exact millisecond you stop pushing? Well, the core explanation here is the inertia of motion. In the simplest terms, a moving body kind of has a mind of its own. It naturally wants to keep moving in the exact same direction it was already heading. It resists any change to its motion. Honestly, it would literally keep going forever unless an external force stepped in to interrupt it. It's an absolutely foundational rule of nature. Which brings us perfectly to Section 2, why bus passengers lose balance. You know, the classic bus phenomenon. We've all been there, right? You're standing on a bus, totally relaxed, minding your own business, and suddenly the driver steps on the gas or slams on the brakes, and you completely stumble. You feel like you're being thrown around. And this brilliantly illustrates inertia in action. Think about it. When the bus starts suddenly, your feet, which are firmly touching the floor, move forward with the bus. But because of inertia, your upper body desperately wants to stay right where it was. So what happens? You fall backward. On the flip side, when the bus stops suddenly, your feet stop with the bus. But your upper body, again, thanks to inertia, wants to keep moving forward at the exact speed you were just traveling. So boom, you fall forward. It's literally just different parts of your body trying to follow the rules of inertia. Moving right along to Section 3, friction, a double-edged force. We're talking about the grip and the slip. You know, we often think friction just slows us down, but it's absolutely essential. It is incredibly useful. Without it, you honestly couldn't walk. Your shoes would just slip endlessly like you were walking on perfectly smooth ice. You wouldn't be able to hold a pen firmly or write a single word on a piece of paper, because the ink actually needs friction to grip the page. And perhaps most importantly, vehicles wouldn't be able to stop. Brakes rely entirely on friction to bring a speeding car safely to a halt. In all these everyday scenarios, friction is a total lifesaver. But there is a harmful side to this story too. While friction helps us walk, it's also the very thing that wears out the soles of your favorite shoes over time. And in machinery, friction is a massive headache. It causes constant wear and tear on moving parts. It generates all this unwanted heat, which essentially just burns up energy, severely reducing the overall efficiency of engines. So we're basically in this constant fight against friction in engineering, even though we absolutely rely on it to survive. Wild, right? That brings us to Section 4, the truth about falling objects, and the classic heavy versus light debate. For centuries, people just naturally assumed heavy objects fall faster than light ones. It makes intuitive sense, right? If you drop a heavy stone and a light feather from a building, the stone obviously hits the ground first. But let's compare falling in normal air with falling in a true vacuum. In everyday life, we have air resistance. As objects fall, they have to physically push through the air. The feather, being light and wide, catches a lot of air drag, which slows it way, way down, while the stone just punches right through it. But what if we completely remove the air? In a vacuum, where there's absolutely zero air resistance, an incredible thing happens. If you drop them both, the stone and the feather fall perfectly together, hitting the bottom at the exact same time. No way, right? But it's true. So the crucial point here comes down to one specific number, 9.8 meters per second squared. That is the acceleration due to gravity. The huge takeaway here is that without the interference of air resistance, gravity pulls on every single object with the exact same acceleration, completely regardless of how much it weighs. A heavy stone and a tiny feather are governed by the exact same invisible force. Finally, we arrive at Section 5, what happens during collisions. We're going to break down the rule of impact.
A crash usually looks like pure chaos, but there are actually unbreakable rules dictating exactly what happens. Let's walk through the timeline of a collision. In step 1, right before the collision, you have two objects approaching each other, and each is carrying its own speed and mass. Then in step 2, you have the actual impact. During this absolute split second, the forces the objects exert on one another are incredibly precise. They are perfectly equal and perfectly opposite. And then, in step 3, after the collision, they separate, carrying away the results of that exact force exchange.
Now, because those impact forces are equal and opposite, we get this beautiful principle called the conservation of momentum. In plain English, it simply means that if you add up the total momentum of both objects before they crash, it will mathematically equal the exact total momentum of both objects after they crash and separate. Initial momentum equals final momentum. It never just disappears, it only transfers from one thing to another. It's a fundamental law of nature just playing out right in front of our eyes. And that brings us to the end of our explainer today. We have explored the secret of continuing motion, the bus phenomenon, the dual nature of friction, the truth about gravity, and the rules of collisions. These aren't just abstract textbook ideas. They are literally the foundation of our physical world. So I'll leave you with this thought. Whether you're sitting in a chair, holding your phone, or just taking a breath right now, how are these invisible forces of inertia, friction, and gravity interacting with you at this very moment? Think about it and stay curious.